All right, we're going to talk about doing double integrals with polar coordinates. So using polar coordinates means doing polar coordinates on the x, y plane. So a point in 3 dimensions space can be denoted by r theta z. Z is the same as the z we already know. The difference is the first two. Instead of x and y, we're going to have r, which is the distance from the origin to the projection of the point onto the xy plane. So this is x, y, 0, this point down here. And so r is the distance from the origin to the projection x, y, 0. And theta is the angle measured positively counterclockwise from the view from the top, starting with the positive x-axis. So that would be theta. And of course, theta is always in radians. So to transfer r theta z into x, y, z is reasonably well known from calculus 2. Many students see this in calculus 2. X would be r cosine theta, y is r sine of theta, and z is z. There's no change in z. So the question is, how do we integrate using polar coordinates as opposed to x, y coordinates, Cartesian coordinates? We have to figure out how to find areas of rectangles. So let me talk about rectangles for a moment. So what is a rectangle in xy coordinates? Xy coordinates rectangle. By a rectangle, what I mean is that the two variables involved are bounded by a finite number. They don't have a variable boundary. So x will be between a and b, for instance, where a and b are fixed, and y is between c and d. And so a rectangle in xy coordinates will look like this, where x can go from a to b, and y can go from c to d. So this looks like a regular rectangle as we know it. A polar rectangle, on the other hand, polar rectangle, and I'm sort of making up this term, a polar rectangle means r is bounded by two numbers, say a and b, and theta is bounded by two numbers. Now, since theta is a Greek letter, I'm going to use Greek letters also for the boundaries of theta. I'm going to use alpha and beta. So these are lowercase Greek letters, alpha and beta. And of course, you already know that is theta. So what is a rectangle? This is a polar rectangle, in quotation marks. A polar rectangle means, looks rather like that. We got an angle that goes, so this would be angle alpha, angle beta, and we got two radius, A and B. So this is what I call a polar rectangle, which doesn't look anything like that. It does have four sides, I guess, 1, 2, 3, 4, but these are curved sides. Now, this distance going up is maintained. It is the same from A to B, and the angle goes from here to here. So this is a polar rectangle as opposed to a XY rectangle. So the concept of rectangle can change. Now the angle, if you take the tangent here of this curve, the tangent of this curve at that point with this will be a right angle, will make a right angle. And so it is a rectangle in the sense that those are right angles. If we take that angle as the angle between the boundary here of the angle and the tangent of the curve. But the curve itself, I mean the side of this rectangle curves, and this is longer than this in distance. In a regular rectangle, those are not. One is not longer than the other. They're exactly the same distance. So be aware this is a rectangle, and this can go all the way around. In fact, a circle, which is kind of weird, a circle is a polar rectangle. A full circle, well, I shouldn't say a circle, a washer is a rectangle. The farthest we can go for theta, though, is from the width of the theta cannot be more than 2 pi, because once you go more than 2 pi, you start overlapping over itself, and we don't really want to do that. So just be aware, theta can only go from, I was going to say from 0 to 2 pi, but it doesn't have to go from 0 to 2 pi. It can go from any angle, pi over 2 to 2 pi in addition to that. So as long as the gap between the two is 2 pi or less, we're good. The radius can be as far as we want it to be. But in order to have a rectangle, we have to have boundaries. And we do in this case. All right. So this is a rectangle, and this is a polar rectangle. Now the area of this is easy. You just find this distance, and multiply the two, and we are all set. When these distances are small, when we are taking, technically speaking, when we're doing partitions and the widths and heights of the partitions go to 0, then we still have the same kind of area. The area here, the area of this rectangle, for instance, is the base times the height. The base is typically labeled as delta x. The height is delta y. So the area of this little rectangle is delta x times delta y. And that's how we use the differentials dx, dy for double integrals. Here, when we split into little bits, it isn't clear how we're going to do that. Notice that if you go out, let me split this into to make the point I'm trying to make here. If you split r, this is the radius, and take the midpoint, and you go out this way, so this distance is the same as that distance. Notice that you don't get the same area. This polar rectangle is bigger in area than this one. There's more to this. And you can see that because if you make this a little horizontal and you draw a line across this way, you're going to see you're going to get much more area. In fact, you get a deficit if you draw a line across. So we do get more area here than here. So finding the area of a sector or a truncated sector of a circle, as in this case, is not as simple as just multiplying delta x and delta y. Yeah, let's kind of split this into little bits. But before that, I want to show you how do we get about getting the area. For purposes of very, very tiny, I'm going to draw more lines, curves here. So pretend you got not regular rectangles, but polar rectangles. So we have a center coming out here, and then we have to draw lines that come off the center. So they get wider rather, as we go out. So this is a polar rectangle. The smaller those rectangles are, the more they're going to look like those rectangles, even though they are not really those. So if you start drawing very, very good, very accurate lines, if you go really, really tiny, in fact, you can kind of start seeing that a little bit because you see less of the curve. You have you don't have as much opportunity to actually have the line curve as much, and consequently, this looks more and more straight. Now, let's pretend this is an angle theta. Yeah. So the angle. Let me draw a new picture because there are things I want to refer to that are not in the picture. So there's the center. Yeah, so the angle is out down here by the center of this picture. There we go. All right. And if this angle is small and this distance gets small, then this polar rectangle looks more and more like a regular rectangle. Now we know from trigonometry that this arc length in a regular circle is r theta, where r would be this distance. Again, so this is r theta, that's from trigonometry. Mind, theta has to be in radians. All of the calculus we do for formula purposes, theta, the angles are always in radians. Otherwise, things get more complicated. We have to multiply by, I believe, pi over 180. And then all the simple formulas we know would have to have that extra factor to work with. Okay, so the area of this region, let's call this just, yeah, delta A. Yeah. So pretend this is small, would be this distance. Actually, it is approximated by this distance by multiplied by this. Why? When those numbers are small, when the numbers are small, this looks like a regular rectangle, and the area of a regular rectangle would be base. So pretend this distance here is a delta r. So from r a little more or a little less. In fact, let's pretend we have a small angle. So let's label this as delta theta. And so let's scratch that. That would be r delta theta. Okay. If the angle is very small, and if this distance is very small, well, particularly if the angle is very small, then the delta A is going to be very much like a rectangle, whose base will be delta r and whose height is r delta theta. Again, it is not a rectangle. So in this case, delta A for the area, the little bit of area, not equal, is approximately, yep, base times height, delta r times r delta theta, which we can reorder. This is a product, so we have commutativity, r delta r delta theta. Yep. So the conclusion of this is if you got a double integral over a general region of a function of two variables, x, y, with respect to the area, we know from previous videos that this is equal to, over the same region, same function, dx dy. The difference is that this is an iterated integral. This is the double integral. So this is double integral, and this is an iterated integral. Well, if we're using polar coordinates, no problem. We have the double integral over the same region of the same function. But instead of having xy, and the reason why we have xy is because a little rectangle's area is delta x times delta y. So when we take the limit, we turn those into differentials. But here, a regular rectangle, well, a regular little section of this area is going to be r, delta theta. So those three parts have to be involved in this integral. R, dr, d theta. So there's an extra r that shows up every time you're doing a double integral and involving polar coordinates so that you can find the double integral. You have to include this extra factor. And the reason is, see, this sector will be much bigger the farther away we are from the center. Yeah, so the angle is going to, angle is going to make the distance between the two sides longer and longer the farther we go, and consequently this is going to get much larger the farther we go. So r has to be included into the picture. Dr and d theta are not sufficient to tell us how big this is in area. So r has to be into the picture. So that's why we introduced that. This has a name. It is called the Jacobian of changing regular coordinates, xy coordinates, into polar coordinates. So every time you want to find the integral and you switch from polar to coordinates to polar coordinates, we have to introduce the Jacobian into the integral, and the Jacobian for polar coordinates will be r. Let's do an example. Okay, so we want to evaluate the double integral of x squared plus y squared with respect to the area over the region R, where R is the unit circle, which is understood to be centered at the origin. So we're familiar with this paraboloid, and we want to find the, well, one way to interpret this is to find the volume of the solid that is under the paraboloid. So between this circle, which is the unit circle, and the surface. So there's going to be a solid. I suppose I can draw a picture of the solid. On the outside is going to be a cylinder. On the inside, we're going to have the paraboloid. So this is going to be the solid whose volume is going to be given by this integral. Yep. The radius is going to be 1, of course. 1. So the top view of the area over which we are integrating is, of course, going to be a circle. If we wanted to use xy coordinates, yeah, I'm assuming this is f. I should have put f, but let's just write it down to be sure over the region. So the double integral of x squared plus y squared with respect to the area over the region. If we wanted to use xy coordinates, we would have to do the integral from -1 to 1 on the axis, and then the integral. Now, a circle has a variable. It is not a rectangle. It is not a xy rectangle, because it has, you know, a regular rectangle has fixed height. This one doesn't have a fixed height. It varies. So this is not a regular rectangle. So we go from negative square root of 1 minus x squared to positive square root of 1 minus x squared plus y squared, dy dx. So that's the way we would do this guy. And that is a doozy, trying to integrate this way. It's not too bad because this is a polynomial, so we would end up with y x squared, or x squared times y plus y cubed. Integrating that is going to give us I'm sorry, x squared y when we integrate, and y cubed over 3, but then we got to plug those in, and it's going to start getting messy for a while if you do this. Can we do this? Absolutely yes. And I, in fact, encourage you to practice doing this the way it is. But this circle is a polar rectangle. Why is it a polar rectangle? Because the points in the circle satisfy that theta is between 0 and 2 pi, and r is between 0 and 1. So if the region, the points in the region satisfy the inequalities in which the two boundaries for the variables are fixed, not variable, so they're fixed, then we have what I call polar rectangle. So this is a rectangle in polar coordinates. Why? Because the variables have fixed endpoints. So can I change that? Sure. So we can integrate from, it doesn't, I guess, let's start with this, 0 to 2 pi, 0 to 2 pi on the thetas, and then from 0 to 1 on the r. Now, something I have to remind us of is what x is. So let me make a note here. Recall that in polar coordinates, x equals r cosine of theta, and y equals r sine of theta. Oh, I did mention that earlier in the video. So x squared. So x squared plus y squared will be r squared cosine squared theta plus r squared sine squared theta. So they both have the same r squared. We can factor that out. Cosine squared plus sine squared, all of us know, is 1. So we end up with r squared. So we're really integrating simply r squared. Dr d theta. The reason why I left a gap here is because every single time we go from regular coordinates, xy coordinates, to polar coordinates, we have to include an extra factor, which is the Jacobian. Okay. And the reason why we have r squared is because we started out with x squared plus y squared. That is the function we are integrating, and x squared plus y squared is equal to r squared. So we're really integrating r cubed. R cubed from 0 to 1 is really r to the 4 over 4. From 0 to 1 is 1/4. And then integrating 1/4 from 0 to 2 pi, which is a constant. So we're really integrating 1 from 0 to 2 pi with respect to theta, and that's going to give us 2 theta. So we get 1/4 from this, and we get 2 pi from that. But notice how easy, very, very easy. So 1/4 2 pi gives us pi over 2. This is the volume under the paraboloid within the unit circle. That's the volume, pi over 2 exactly, no more, no less. That's it. And again, the integration was very, very, very smooth. Yeah, yep, yep. Let's do, I was prepared to do a simple example, but as I was working on this, I realized we could have examples where we don't have a polar rectangle, but some kind of surface, or rather some kind of region that is not a rectangle, even in polar coordinates. So let's do an example 2. Okay, so find volume of solid under a z equals x squared plus y squared over region R, which is all the points x, y, such that like x, y on the xy plane. Let's see, where theta is between 0 and 2 pi, and r is less than, let's put sine, or rather 2 plus sine of theta, less than or equal. Okay, so let's draw the region that we are integrating over. So when theta is 0, 1, 2, we are here because we're adding nothing to it. When theta is pi over 2, we go up to 3 because we're adding 1. So as we sweep an angle starting here, going up to pi over 2, the sign turns 1. 1, 2, 3. So now we go up to 3. So we start at 2, up to 3. Then 2 pi, we get again 2. So this is 2, 3, negative 2. And then when we have 3 pi over 2, sine of 3 pi over 2 is negative 1, but then we're adding 2. So we go out to 1. So we have this kind of region, sort of like a cardioid. Some kind of nut. There we go. All right. So this is the positive x-axis, positive y-axis. So this is what's going on. We got a paraboloid, but we're not going to integrate over a circle, a perfectly nice circle that will give us a beautiful cylinder. No, 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 no. This is way, way more complicated because there is the x-axis, rather, the y-axis. So on the x-axis, let me exaggerate the picture a little bit, the 2s and the 3. So we go from 2 to 3, and then here only to 1. All right, so this picture, this is going to go up to here. This is going to go higher because it goes farther out. So, and who knows how this is going to look. And then here in the back, it's going to go low. Yeah. So we have something going on like this, and then around. Yeah. So the question is, what is the volume under this? And that is not obvious. That is not clear. So we want to find the double integral of x squared plus y squared, yep, with respect to the area. That's going to give us the volume. The volume is a double integral of height with respect to the area over the region. The region is this, which is down here on the floor. Yep. Well, from the previous, so we're not going to do this with XY coordinates. Figuring out the top and the bottom, at least with the circle, we had some idea. I kind of just told you this 1 minus x squared positive and 1 minus x squared negative. The top and the bottom, we should know that. Here, I don't even know. I have to figure that out. It's not going to be pretty, I think. Yeah, who knows what it will be to figure this out. The top, boy, I keep thinking about it, and the bottom. So we would have to multiply by r if we make those two equal to each other. So r sine is y, and r squared is x squared plus, there's a way to do that. In fact, I'm very curious, but let's move on and try to find the value. So from the example one, we know that this is going to be r squared. There's no need to redo that part. So one integral from 0 to 2 pi. But then the second integral, or the first integral, as we go from the inside out, is we're going to integrate out this way from 0 to the boundary, which is variable. It is 2 plus sine of theta. 2 plus sine of theta. Yep. R squared. But then because we are changing dA into polar coordinates, or the coordinates into polar coordinates, but we're integrating with respect to the area, we have to introduce r dr d theta. So this r dr d theta is what replaces dA. Yep. Now, of course, those two multiply, we get r cubed, and then we have r to the 4. So we have the integral from 0 to 2 pi of r to the 4 over 4. At 0, we're going to end up with 0, so we end up with 2 plus sine of theta n to the 4 d theta. Whoa, this is way more difficult than what I was anticipating. Yes, this integral is kind of long, but it's not that difficult after all. First, I'm going to FOIL this out. And again, by folding, we mean multiplying it out. It does take a few minutes, but we end up with 16 plus 32 sine of theta plus 24 sine squared theta plus 8 sine cubed theta plus sine to the 4 theta. And we got to integrate this with respect to theta. And you may be thinking, whoa, yes and no. So first, 16 is a constant, so that's just going to be 16 theta, plug in 0 to 2 pi, so we end up with 32 pi. So I'm going to do this in parts. So the 16 is taken care of. 16 is going to turn into 32 pi. Sine of theta, now think about that. Sine of theta is just your regular wave function. If we integrate from 0 to 2 pi, never mind the 32, but just the sine of theta, you're going to get 0. So these are some side work. Okay, if you integrate from 0 to 2 pi sine of theta with respect to theta, well, just think about it. It's just sine. So whatever this is positive, which is 2. Whatever this is negative, cancel. So they add up to 0. So this guy is going to be 0 after we integrate 0. The cubed is going to be the same. The cube is going to be some kind of curve that is going to stay positive. So who knows how it's going to go up here, but it's going to go from 0 to 1, down from 1 to 0, because when we cube numbers, we preserve the sign of the output. And the same thing is going to be here, except that the negatives are also going to be negative. The negatives cubed are going to be negative. So the picture is not going to be exactly like this. It is going to be similar to this. This is an add function, a periodic add function. So when we go from 0 to 2 pi, we're going to end up with 0. So this guy is going to be, after we integrate, we're going to end up with 0. So we don't have to worry about those two terms. This is a well-known function, reasonably well-known. Let me just show you how we did this back in Calc 2. So 0 to 2 pi. So that is, we do apply some trigonometry. So this is 1 minus cosine of 2 theta over 2 d theta. Now think about that. The same argument applies to the cosine. We got two full periods. The frequency of this increases by 2, starting from the regular frequency of 1, I guess, or 2 pi. So the frequency, the period is 2 pi. The frequency is 1 over 2 pi. So now with this 2, we have 2 of those. So we got 2 waves from 0 to 2 pi. And so that's going to be 0 because the positives and the negatives are going to add up to 0. So we really have just 1/2 of 2 pi. So this is half of 2 pi, which is just pi. So each one of the integrals of sine squared from 0 to 2 pi is going to be a pi. So these guys are going to be a pi each. So we add 24 pi's. That's going to be the longest one to work out the integral of sine to the 4 theta d theta from 0 to 2 pi. Let's see. So we can break that up into sine squared theta. The other sine squared, I'm going to write as 1 minus cosine squared theta, which is true, from 0 to 2 pi. Let's distribute. After we distribute, we can break up into two integrals. So we have the integral from 0 to 2 pi of sine squared, which we already know the answer to. It is pi. That's right there. Minus the integral from 0 to 2 pi of sine squared theta cosine squared theta d theta. Okay, so that is going to be pi minus the integral from 0 to 2 pi. That is really 2 times sine cosine of the same angle is really the sine of double the angle. Because we don't have the 2, we have to make up for that, but we got those 2 squared. So we really have sine of 2 theta squared d theta over 4. But then the sine squared, using the same trigonometric identity we applied here, is going to give us, let's see, pi minus the integral from 0 to 2 of 1 minus cosine of double this angle, 4 theta over 8. Technically speaking, it should be over 2, but we already had a 4 in there, so that's how we get an 8 d theta. Okay, well, the same argument we applied here about the positives and negatives adding to 0. We got 4 full cycles of cosine from 0 to 2 pi. I'm missing the pi here. 4 full cycles. So when we integrate those cycles, we're going to end up with 0. The only thing that survives is the 1/8, which we multiply by 2 pi. So we really have pi minus 2 pi over 8, which is a quarter of pi. So that is really 3 pi over 4. So each one of those sine to the 4 is going to be really 3/4 of pi. Going back to our computation here. So we add, oh, that happens just once. So 3/4 of pi. And then we add those together. 32 plus 24 is 56. So we have 56 3/4 of pi. Well, 56 times 2, because we want to have a really nice fraction. 56 times 2 is 112. 224 plus the 3 is 227. So this is 227 pi over 4. There we go. So the other thing that took a while was to FOIL this out using a Pascal triangle. That's what I used to figure out the coefficients. I was able to do this. It took about 2 minutes to figure this out. And then once you have that, some of those terms are going to be 0. The other ones are reasonably easy to obtain. Even that one wasn't too bad. So the volume above this cardioid and below the paraboloid is exactly, no more, no less, and exactly 227 pi over 4 cubic units. So this is an example of a, an integration using polar coordinates where the region we're integrating over is not a polar rectangle. How can you tell a polar rectangle from a non-polar rectangle? If you got constants all over, then you got a rectangle, a polar rectangle, even though it doesn't look like a regular rectangle. Um, and if you have variable ones, then you don't have one. Doing this with Cartesian coordinates would be even more difficult than it is. This was already difficult enough. And with this, we will stop this video.